Let's work this example. The average age of a female in the U.S. gets married is 27.4 years old. A researcher thinks it's older in her community. She randomly selects 36 married females from her community and compiles a data set. Search on women's age at marriage in Statcrunch. Is this strong evidence to support her belief? Use a 0.05 significance level. So I read this problem. I don't get the traditional sort of summary of the evidence that I've gotten in many of my problems thus far in the course. Instead, we're told to go resource some raw data in Statcrunch, which we will do. So before I do that, I kind of want to think about, like, is this problem about means or proportions? A common question I ask at the beginning of a hypothesis test. If I dissect some of the language here, the second word is average. And I also see the idea of an age, which is a measurement, not necessarily a categorical variable. And so I'm thinking about this, and I'll sort of double check this when I actually look at the data in Statcrunch. But my hunch is that the word average here and having a measurement as the data, this problem revolves around means. So I will be using our parameter mu when we write the hypothesis statements. Before we jump in the data, let's get the hypothesis statements written. So the hypothesis statements here, we'll have a null hypothesis and an alternative hypothesis. As I mentioned, they'll both have a mu in them. What was that age again that U.S. females get married? 27.4 years old. I will go into my hypothesis statement. Oops, sort of hastily put an equals to in there. That's not supposed to be there. The 27.4 is repeated in the second hypothesis as well. And the researcher's research question, or her hunch, is that the people in her community, the females that is, are a bit older than the national average. So here's our hypothesis statements. We want to check some assumptions and conditions here, just to make sure we know where we're heading when we do the mathematics. If we are testing one mean here, as we are suspecting, we need to see if these conditions and assumptions check out. So did the researcher use a random sample? And in fact, she did. She used 36 randomly selected married females. We're going to have to assume that each person's age at their first marriage is independent of the next. I think that's easy enough to assume. And is our population data normally distributed? It's my little bell curve here, is shorthand. Or is our sample size greater than or equal to 30? Well, we weren't told anything about the population data, but we do know that the researcher used 36 in her sample, so it checks out. The sample size is clearly bigger than 30. So all of these assumptions and conditions checking out means that we are going to use the t distribution to solve this. Let's head to Statcrunch. Here we are in Statcrunch. To access this data, you're going to want to go to Statcrunch opening screen and click on Data Sets. This gives us access to all the public data sets in Statcrunch. I'm going to type in the search terms, women's age at marriage. Here it is. If we open it up, we now see the researcher's evidence. And as we suspected, they are indeed the ages reported by the 36, as we see here, yes, 36 different women. So our testing this as a mean was completely correct. Now, I want to do my hypothesis test, and there's a way to do this without that traditional summary. Let me show you. So we're going to still navigate to Stat, t-stats because we're using the t-distribution while testing means. One sample, and if you notice here, we have the option with data, which is the situation we find ourselves in. So instead of entering 3 pieces of information we typically got within the text of the problem, we're just going to give Statcrunch the entire column of data. Now it's sort of easy in our problem. There is only one column of data in our data set, but if you get to a data set where there's many, you just scroll through the list of the one you need and then advance it over. We're still going to have to set up the hypothesis statements. You can see because we chose t-stats, we have a mean here, and at 27.4 years of age and greater than. So much like our last one, evidence in the form of raw data coupled with the hypothesis statements, Statcrunch can handle the mathematics for us. We'll hit compute. Here we have our results, the hypothesis statements repeated back to us. Double check everything's correct. The age at marriage was the variable it used. And if you were curious, in that particular community, the average age or mean age of those 36 women was 27.9 years of age. So they are a little bit older. The question is, are they significantly older than the national mean or national average? Well, the t-stat and p-value will help us determine that. So here is the t-stat. Had I sketched this out, I would have seen that less than 1 tick mark to the right, less than 1 standard error to the right, our sample mean would be graphed, which means that the mean of this population or this community is not that much different than the national mean. And we would also see that the p-value there is quite large at 0.247, 0.247. And I can't help but draw a quick sketch here, and this will be a very rough sketch here. But if I have a bell t distribution here, be centered at 27.4, 3 tick marks away, our data would come in just about here, I would say, at 27.9. Remember, the t-stat was 0.69, so it's not even 1 standard deviation, pardon me, 1 standard error to the right. And then this would be my p-value, which was 0.247. This is the p-value. So always like to connect these things back to pictures if I can. So that would be a rough sketch of what we have going on. And this being that less than 1 tick mark away, which corresponds to our t-stat, equal to 0.69. Excellent. All right, let's make a decision here. Our p-value is 0.247. Our significance level, as stated, is 0.05. So we have to make a comparison here so we can figure out whether to reject the null or retain the null. Our p-value is much bigger than our significance level. It's almost at 25% here at 0.247, and a 5% is where we would draw the line at unusual. So our p-value is clearly greater than our alpha. So that means we will retain the null. And as you can see here, our data is not all that different. Going back to this picture again, not all that different than the national mean. So this is not compelling evidence. This value, 27.9, deviates a little bit from the national mean, but not enough to discount the truth of the 27.4. Alrighty. Before I write my statement, I always like to re-establish my null and alternative. Get them somewhere close by I can see them. And try to remember what it is we're doing. Right? Everything revolves around these two statements. So again, we were told to retain the null. So I like to circle that here. That's what we're walking away from this testing process with, the idea that the mean in this community is essentially similar enough to 27.4. So can't go with the alternative. This is what the researcher, this was her idea, right? That was her idea. And my data is not supporting that. So I'm going to say, kind of think about that a little bit in my brain before I start to write a statement. Here's the completed statement. The sample data suggest that the average age of females' marriage in this community is not older than 27.4 years of age. So again, I'm just sort of speaking to my findings here. I was not able to go with the researchers' hunch, had to stick with the null, which is saying that the data did not support her belief. These females are not significantly older than 27.4 years of age at first marriage.